So we here on Earth are kind of at a disadvantage, obviously, to studying things that are far away, like stars and nebula, let alone galaxies, to understand the structure of the universe. So we are relying on those objects sending us information. They are cosmic messengers, and they do that by sending us light. But they also send us other forms of energies. We're going to talk about different forms of radiation, and light is one form of radiation that they send us. And so what you're looking at here actually is kind of information from our sun, actually. And those black lines we call spectral lines, and they tell us what our sun is composed of. So light, one of the things that Newton found is that if you take white light and you pass it through a prism, you will get, in white light actually is a mixture of all the colors of light. And so one of the experiments that he did was actually after you take, I think he did it, after you take white light and break it up into its components, what if you take a component and pass it through a prism again? What happens? And what he saw is that it's what we say bent again through the prism. Its direction changes because of the prism, but it is still just that one component. So anytime we see light coming from, white light coming from the sun, or white light coming from a light bulb in the room, that is actually has all components of colors, all colors in it. Okay, and light is just one form of a group of energies we call electromagnetic radiation. And just like we call this kind of we call the rainbow the spectrum of light, so also we call all the families of energy, including light, the electromagnetic spectrum. So let's take a look at the electromagnetic spectrum. All right. So you might recognize some of these names, and I'm kind of trying to pull up my pointer here, or am I able to draw? Okay, here's a figure from your textbook, and I really like it. So here, just in this little region right here, is visible light. But I'm sure you've heard of UV, ultraviolet light, okay? And kind of from right back to left, in this case, they're getting more intense. So ultraviolet rays, more intense than ultraviolet rays, are X-rays. More intense than X-rays are gamma rays. And when I say more intense, I mean literally there's more energy associated with those wavelengths, or with that form of energy. Notice the other thing. Can you see where it's like a squiggly line, and we're going to see that all electromagnetic radiation goes or travels in waves, and that's what's showing you here. But can you see where the distance of the wave gets shorter as you go from less energetic to more energetic? Okay, so the shortest wavelengths here are gamma rays. So one of the things that I want you to know about in this chapter of material is this idea, this family of radiations, this family of energies we call electromagnetic radiations. All right, so let's get longer wavelength than light. And here you go. You've probably heard of infrared. Infrared, actually, part of infrared is thermal energy we call heat. So infrared is longer wavelength than visible light, and then even longer than that are microwaves, and even longer than that are radio waves. So you can kind of see how that works. See, these are all families, different energies that are part of the family of energies we call electromagnetic radiation. So together they make the spectrum called the electromagnetic spectrum. So we have wavelength changing. We have the shortest wavelength over here, and we have the longest wavelength over here. All right. Now, frequency is another way to talk about different types of radiation. So down here, now frequency, in order to understand frequency, I've recently come across or thought of this, and probably somebody told me to think of it this way, but basically, if you're standing still, we're going to see that radiation is going to, what we say, propagate through space. So if you're standing still, this radiation is going to pass you. Okay, this is you. You are the You are the asterisk here, and the radiation is going to pass you. And you are going to count the number of cycles, okay, complete cycles that pass you. There's 1, okay, there's 2. And by the way, all electromagnetic radiation travels at what we call the speed of light, or specifically the speed of light. So here's the deal. Here you are counting cycles that pass you. So frequency is in per minute, or excuse me, per second, sorry. Hertz are per second. So can you see where if I have gamma rays that are passing my location, that I'm going to get a lot of them in a second? And if I am counting radio waves that pass me, can you see where I'm going to get not very many per second? So that's why the frequency for gamma rays is high. High frequency means you count a lot per second. And the frequency for radio waves is low. There's not very many that pass per second. Does that make sense? Now up here, and I didn't mention it, but I like what your textbook does. It kind of says with regard to wavelength, okay, remember, well, I have a slide coming up, but wavelength is the distance between a repeating unit. So we call this a crest. For instance, I'm looking at the radio waves, and we call this a crest. This distance here would be what we call the wavelength. And the symbol for wavelength, I have it coming up on a slide in case you can't see this, but is the Greek letter lambda. But for instance, the wavelength here in kind of the microwave radio region, how long is a repeating unit? Oh, about the size of a baseball, perhaps. We get down here into longer radio waves. How long is a repeating unit? Oh, about the size of a football field. Okay. Visible light, when it kind of cycles through, okay. What is this distance? Well, about the size of a bacterium. Shorter than that, ultraviolet X-rays about the size of a protein. X-rays about the size of a hydrogen atom. Okay, so that kind of puts things into perspective. Public viewing, or when I'm outside trying to show people the constellations and stuff, I use a green laser light. And the green laser light, let's see, find green in here. Okay, green laser light is a wavelength of about 520 nanometers. 520 nanometers. So that's the distance between two repeating units of that color of light. So one of the things, maybe you buy it, maybe you don't, but all objects ooze, they emit radiation. All objects emit, and oftentimes a variety of information, electromagnetic radiation. So for instance, a light bulb emits, if it's a white light bulb, emits all colors of visible light. People, okay, although they can reflect light from a light bulb, people ooze in and of themselves. They ooze a certain amount of infrared radiation, which I said was heat. Okay, these are radar, microwave oven, ooze those longer wavelengths. A radio transmitter oozes radio wavelengths. Okay, X-ray machines. Radioactive elements are harmful in that they can actually emit some of these shorter energetic types of energies. Well, the last row here, I think this is pretty neat, actually says, all right, but we're studying astronomy. What sort of celestial objects are we going to be looking at as we try to, as they are behaving as cosmic messengers, who's going to be emitting gamma rays? And we're going to talk about this phenomenon called a gamma ray burst, which we think might signal the formation or the activity of a black hole. Who doesn't love black holes? Also, black holes can give us X-rays. We study the sun in ultraviolet. You know, let's see, this is a cool one. When we look at remnants of the Big Bang, we look in longer wavelengths. We use radio astronomy to map other galaxies, or our own galaxy too. Okay, so Electromagnetic radiation, all forms, all different, we looked at gamma rays, X-rays, ultraviolet, visible, infrared, microwaves, radio waves. They all have these things in common. One of the things is that they travel in waves, and waves have a few things. We have the crest of a wave, and we have the trough of a wave. And I mentioned that we use the Greek letter lambda to tell what the wavelength is. So one of the things I want you to kind of get a handle on is, like I said, that radio waves have a long wavelength and gamma rays have the shortest wavelength. Okay, so now all energies, all electromagnetic radiation, all forms are traveling through space, and they're traveling at the speed of light. They have different wavelengths, but they are also traveling in these cute little packets of energy we call photons. And that's what these little E's are showing you. These E's are little photons, little packets. And if we isolate a photon, a gamma ray photon, we're going to see it has more energy than a radio wave photon. Okay, but they are both the gamma ray photon and radio photon are traveling at the speed of light in a wave sort of function. Okay, I just think it's amazing. Okay, so we use the Greek letter lambda. It looks like an upside down V with kind of a tail on the top as wavelength. And we use like kind of a script F for frequency. Remember what frequency is you're standing there and you are counting cycles or waves that pass you per second. Okay, so when somebody talks about 1 hertz, that means that 1 cycle has passed you per second. So for instance, if you're tuning your radio dial into a certain station, you will turn your radio dial to a certain frequency. And you are isolating that particular signal in that way. It has a specific wavelength and frequency. Well, as frequencies get large, what we do is add this metric prefix called giga. And giga in the metric system means 1 billion times the base unit. So, for instance, here we go. I'm going to kind of compare 3 different scenarios, 3 different forms of radiation. In this first one, I want to show you that it has a wavelength of 1 centimeter. That's something you can sink your teeth into. So it has a wavelength of 1 centimeter, and it has a frequency of 30 gigahertz. So that means it has 30 billion cycles per second. So if you're standing there being a counter, in 1 second, 30 billion cycles will have passed you. Isn't that cool? Okay, so let's look at another form of radiation. Notice that its wavelength is shorter than the first one. We'll call this A, and we'll call this energy B. Notice that its wavelength is shorter, so what happened to its frequency? Instead of being 30 gigahertz, it's 60 gigahertz. Specifically, its wavelength is half as long, so that doubled the frequency. Does that make sense? I think so. Well, let's look at one more, and we'll call this C. And if we compare A to C, C has a wavelength of 0.25 centimeters, so we're getting shorter wavelength. Okay, so we must be getting more energetic forms of radiation, shorter wavelength. And notice that with the shorter wavelength, what it did was increase the frequency. Specifically, since 0.25 is 1/4 of 1, okay, it actually then, the frequency was multiplied by 4. So see how this works? So we have the short, up at the top, from A to B to C, we have the A has the shorter or the shortest of the 3 wavelengths, and it has the oh, sorry, no, I meant to relocate this, darn it. This actually, I meant to relocate down here. Because what I want to say is emphasize this trend, this red line that I showed. What's happening is the wavelength is getting shorter and the frequency is getting greater. Sorry. So to kind of summarize that, we have the longest wavelength up here and the lowest frequency. And down here we have the shortest wavelength. Oh, darn it. Shortest frequency, or sorry, shortest wavelength, and we have the greatest frequency. This should have been frequency, darn it. We say that wavelength and frequency are inversely related. So that means as one goes up, for instance, wavelength increases, the other goes down. And down here, we have the shortest wavelength that's going down, and we have the greatest frequency. I did lambda there too. Dang it. Okay, so there's kind of a really cool relationship for all forms of electromagnetic radiation. For any given wavelength or for any given energy, if you were to take the wavelength of that energy and multiply it by its frequency, you will get the speed of light. Okay, so put in another way, in a nutshell, for any form of electromagnetic radiation, this is the relationship that exists. Isn't that cool? I think so. Well, if you were to isolate, just focus on light, visible light, you know that visible light has all colors of the rainbow. And actually, if you go ahead and this is a mnemonic device, if you think of the name, Roy is the first name, G is that guy's initial, and his last name is Biv. What you have done is now you have letters of the colors of the rainbow in order of longest wavelength is red and shortest wavelength is violet. Okay, so Roy G. Biv. It's a thought. So I'm debating, yeah, let me go ahead and play this for you right quick. This is, if you're using Mastering Astronomy, this you should have available to you, and it just basically you can use the slider to go to different wavelengths of energy in the electromagnetic spectrum, and then if you focus down here, kind of as I change the slider, see what happens. So for instance, right now I am in the ultraviolet region. Is this gonna, I think it should, yeah. Right now I'm in the ultraviolet region, and I'm gonna kind of wiggle it back and forth. You see frequency and wavelength are changing, but speed is not. Notice what, and it's in what we call scientific notation, so it might be kind of hard to follow, but let me go all the way to the shortest wavelength of energy. And if I go back and forth, you see that the frequency is increasing and the wavelength is decreasing. Well, let's go clear over here to radio waves, okay, and can you see where the frequency decreased but the wavelength increased?